rather belong to the introductory workshop in summer, but since I wasn't able to come in summer and I was able to come now, I give it now. It's a kind of invitation to discrepancy theory, so it's not so much for the experts who know all the problems I will be talking about and all the results, because nothing in this lecture is very new and most of it is quite old. But I believe that it's worth reminding old things time to time, and also that's precisely the reason why I decided to give this kind of talk, that nothing much has been happening in this area in last year. So there were results, but there are the major problems that have not been moving forward at a good speed. So I would like to encourage, of course, everybody to go and solve the main problems. And so let me indeed start from the very beginning by the question of van der Korpelt from the 30s, who asked whether there is an infinite sequence in the interval 0, 1 that is justly distributed. Justice cannot prevail so easily, so the answer is no. And the geometric formulation of this problem is this one. So is there a constant such that one can, for every n, one can place n points into the unit square in such a way that if you take an axis parallel rectangle like this, then the discrepancy of this rectangle will be at most this constant, where what is the discrepancy? Well, it's the numbers of points that actually are in R in this rectangle R minus the number of points that should be there ideally. And what is the number that should be there ideally? Well, it's n times the area of this rectangle. So this square has area 1, and the rectangle has some area like 0.37. So if you throw in n points at random, for example, then you expect this many points, and so the deviation is the discrepancy. And the question is whether the discrepancy can be bounded as by a constant. And so the answer is no, which was proved by Van Ardenne Ehrenfest. And then in 54, Klaus Roth found a beautiful proof that can be shown even on Friday afternoon at the beginning of such a lecture. And again, reminding old things is sometimes good, so let me just recall this proof. So the first thing is that we won't look at all rectangles. We will just look at what's called anchored boxes. So these are that have the left lower corner at this corner of the square, and the right upper right corner is determined by a point x. This is actually no loss of generality, because the discrepancies of other rectangles can be bounded in terms of these kind of rectangles. That's fine. And we write d of x is the discrepancy of this particular rectangle determined by x. So explicitly is the number of points here minus n times x1, x2, which is the area of this rectangle, which looks like a square on this picture, but this is just a coincidence. And notice that there is no absolute value in this definition. So the discrepancy in this case can be positive or negative. And what the proof does is it is supposed to bound the worst case value of the maximum of absolute value of dx, and actually bounds the quadratic average. So the integral of dx squared over this rectangle. And it will be shown that this integral actually is at least log squared n, and therefore there is a point x for which the discrepancy of the particular rectangle at x is at least the root of log n. Yeah, that's my plan exactly. Yeah. So the heart of Roth's proof is to choose a suitable magical auxiliary function defined on the square and depending on the point set. So the point set is given by the enemy, then Roth constructs the function, and then everything works out nicely. And then one uses Cauchy-Schwarz inequality in this integral form. So the conclusion kind of will be, so if we can show that that this magical function f is such that the integral of f squared is small and the integral of the product, the discrepancy function d times f is large, then the conclusion will be that the integral of d squared will be large. You can just see it from this inequality. So the concrete goals are to show that, to construct this function in such a way that this L2 norm is square root of log n, and at the same time one can show that the discrepancy this product is at least log n, and this is what this will do the job. So here are those functions. There will be m of the functions where m is such that the power of 2 to the m is between 2n and 4n. So you need somewhat more than n. N is not enough. So 2n and smaller than 4n. And the function will be a sum of m functions, one for each index. And the ith function looks like as is indicated in this picture. So how to read this picture? You subdivide the square into 2 to the I pieces vertically and 2 to the m minus I pieces horizontally. So there are 2 to the m pieces, slightly more than 2n pieces altogether, right? And then some of those little rectangles contain points of p, and at those little rectangles the function will be identically 0, this small fi function. But because we have more rectangles than points, there are many rectangles that are empty, and on those rectangles you put such a cross. So you subdivide it further, and the function will be +1 in those two quadrants and -1 in the two other quadrants. Now, these were the goals, that f squared has a small integral. This is because of orthogonality of those small fi's. So it's easy to see that integral fi fj is always 0 for I different from j. Well, you just overlay those two grids, and what always happens that, well, things compensate nicely. I don't want to go to details, but you always have the same area with +1 as with -1. So the integral of f squared is the sum of all those integrals, but the terms with different I and j are 0, so you actually have only the integrals of fi squared, and fi is at most 1, so this is at most 1, each of those little guys, so at most m plus 1 together. This is what we wanted. And now the key part of the analysis or of the proof is to analyze what is this integral of the discrepancy function times fi, and this is the magic of the proof, that this fi is constructed in such a way that the discrepancy, which is in general has arbitrary sign, will somehow be collected together, and you always get something positive. Actually, what happens that this integral will be at least some small constant. I'm using this double inequality sign in the sense where one also uses big omega, so at least some positive constant times the right-hand side. So it doesn't mean it's much larger than 1. It means it's at least 0.0001. So a small constant. Anyway, so this fi is constructed cleverly so that it picks up somehow the discrepancy and makes it in some way positive. And how does it work? So we look at one of those windows. I don't want to violate any trademark, but I hope that this word can be used even in this context. So how does it work here? So this function fi is positive here, negative here. And we multiply it with the discrepancy function, which has some behavior that we cannot quite control. But as we do this integral, we always kind of tie those 4 points together, where this is this window. So this is kind of, let's say, the controlling point which runs through this lower left corner, and these 4 as actually 3 associated points are at the always at the same position in the 3 other rectangles. And it turns out that the discrepancy function kind of combines nicely. Most of it cancels out in each such 4 tuple, and what remains is the discrepancy of this little rectangle. But what is the discrepancy of the rectangle? Well, number of points of our set inside, which is 0 because this window by definition of Fi is empty, minus the area, n times the area. So the discrepancy is something, well, I probably got the sign wrong here, so I would probably need it with the opposite sign or something. But anyway, the sign is always the same, and the contribution is of this little thing is of the order 1. So the contribution for one little rectangle for one of those windows for one Fi is of the order 1 over n. We have at least n of those windows, and altogether we get a contribution at least a small constant. So if we sum this up altogether, we get at least m, which is of the order log n as promised. So this is Ross' beautiful classical proof. And what are the problems related to it? So this is kind of the classical problem in discrepancy. This is how discrepancy theory started, and also it's the most studied one. So it's kind of annoying that it's still far from being solved in higher dimensions. So what is known, then if you are in fixed dimension D, then the L2 average, as in the previous proof, and also the LP average for every fixed P has the order logarithm of n to the power d minus 1/2. And this is what this is exactly what Ross' proof does. So one cannot hope to get any better lower bound for the discrepancy by a method based on averages. This is sharp. There are several constructions of point sets attaining this kind of bound. But in the worst case discrepancy is known only in the plane, and in the plane it's known that it's considerably higher than the L2 average. So there is a strange situation that we can make a point set that most of the time the discrepancy is very good, but there must be some points where the discrepancy is much worse. And this proof, there are several proofs actually of this, but it does the mechanism kind of does not generalize into higher dimensions. So what is known about the worst case discrepancy is that it at most log to the d minus 1, and there is a lower bound which is just a bit better than this lower bound of Ross. So this log to the minus 1/2, which is what you get from Ross' proof, times a function going to infinity, but rather slowly. It's a log to some small power. And so it's a complicated proof and great achievement to get even this, but one would suspect that so actually most people, I think, working in this area believe that this, or I don't know, I haven't polled their opinions, but that this is the right exponent. But
isn't achieved by random choice?
No, random choice won't work at all. Random choice would give you square root of n, not logarithmic number. So I can't cover everything, so there are many nice constructions, but all of them achieve this power d minus 1. But so what the authors of one of the first books about discrepancy, Beck and Chen, called the great open problem is to determine how does this really behave in dimension 3 for fixed small dimension. Is the exponent d/2 or rather d? If I should make a conjecture, I personally believe that it should rather be d/2 and that there should be some nice semi-random construction. But of course, if I knew how to do it, I would not present here an open problem, but the solution. Yeah, I have omitted to spell out the names explicitly, so these are the main people who did these things. And my references to the literature and so on will be very, very scarce, so I would like to apologize if anyone feels offended by not being cited. Then it was not intentional, it's just for time and space reasons. Good, so a general setting of discrepancy. Now we go from this very concrete problem, which originated in number theory, to an abstract general question where we have some ground set X, which can be finite or infinite, any kind of set. We have some system of distinguished subsets on X, and we have some measure on this set X, such that all these sets are measurable. And we are given some number n of points, and our goal is to place those n points in such a way that they approximate this measure mu on this system F, on all sets of the system, as well as possible. So this is the goal. Or technically speaking, we can say that we look for another measure nu that this time is concentrated on n points. This is a bit different because this would allow also for giving weights to points, but really the difference is not that crucial. One has to choose some normalization how to measure this error of this approximation, because obviously if you multiply this measure mu 100 times, then the error also changes 100 times. And the typical normalization in discrepancy theory is that we measure in units of points. That means that the measure of all x is n. This is a somewhat arbitrary or illogical sounding convention, but then the formulas for the discrepancies in the typical settings come out nicely. So you get, for example, log n for the planar case, and not log n over n as you would if you were measuring the most natural thing, perhaps the relative error. So the discrepancy in this general setting is just the worst case over all sets in this set system of the correct measure minus the approximation by the discrete measure concentrated on n points. So the classical case is that we have the unit square or unit cube in higher dimensions. F is the system of all axis parallel rectangles, and mu is just the Lebesgue measure, well, strictly speaking, multiplied by n, right? Now there is another setting that looks very different from the classical one, where we approximate Lebesgue measure but fits more or less under this general description, general formulation, and this is the combinatorial discrepancy or red-blue discrepancy or whatever else it can be called. There, to fit it into this framework, we can say that X is a set of 2n points, F is our favorite set system on this X, and mu is just the counting measure, the number of points. So maybe we could divide it by 2 to get this convention that the measure is n, but this doesn't matter much. And then this approximation question is equivalent to the usual formulation of combinatorial discrepancy. We want to color the points of X, each of them either red or blue, in such a way that the maximum imbalance in a set is minimized, where the imbalance is the number of red points minus the number of blue points used in that set. This is not 100% equivalent, but up to some small, well, maybe a factor or something like that. So it's basically the same question. The traditional notation for this is the disk of F, where F is the given set system. And there is such a hybrid case where we look at the combinatorial discrepancy in this sense, but the set system is given geometrically. That means we would have a system, a set of X would be geometric, a finite set of geometric points in Rd, and then F is a finite set system, but it's induced on our given point set by some class of shapes like axis parallel rectangles. And there is a close connection between those two settings, which roughly speaking says that if we can color well, then we can also distribute the points well with respect to the Lebesgue measure or any other measure. So here is a more detailed formulation. If every endpoint set can be colored red-blue such that the combinatorial discrepancy of the resulting system is at most f of n for some function n, then the discrepancy of that class of shapes with respect to Lebesgue measure, that means you want to distribute points in the unit square, let us say, in such a way that each shape of our class, the Lebesgue measure is approximated, then this kind of discrepancy is also of the order Fn. This doesn't work for some very small discrepancies or very, very weird functions, but generally one can say that this is true. So here is again this principle that if we can color well red-blue, then we can also distribute points uniformly. So the conclusion is that these two things, this combinatorial discrepancy in geometric setting and this Lebesgue measure discrepancy, so uniform distribution of points, are related, and the upper bounds go in this direction. If we can color well, then we can distribute well. Lower bounds can go in this direction. So if we have a lower bound in this setting, then also there is a point set that cannot be colored red-blue very well. And actually, for most classes of shapes like circles, copies of a fixed convex polygon, some other classes like this, ellipsoids, whatever you can think of. This is really how these bounds go. So there are for most classes of shapes, one can say that there are better methods for the combinatorial case than for the Lebesgue measure case. So the most uniformly distributed point sets with respect to these classes are or can be usually obtained via this combinatorial approach by this red-blue coloring. On the other hand, lower bounds sometimes can be done directly for the combinatorial case, but usually again it's easier to work in this Lebesgue measure discrepancy. So this is some kind of explanation of the setting and the basic facts, and now come the questions. So one annoying thing is that the classical case of axis parallel boxes is kind of exception from this little rule here, that this is one of the few cases where the combinatorial methods are weaker than the methods for constructions of well-distributed sets, and the best constructions here cannot be quite matched by combinatorial constructions. And another thing is that there is for the combinatorial bound, there is not strong enough lower bound. So for the combinatorial case, the best lower bound is obtained from this Lebesgue measure case, from this Roth's proof or its improvements. So it would be nice to find some very direct proof. So there is a work of Chazelle and Lvov which is relevant here, but still it leaves something to be desired. So this is a very general problem. The concrete problem, one of old again and classical and open problems, although not as old as this great open problem about the discrepancy of rectangles, is what is the red-blue discrepancy for rectangles. That means, again, you place endpoints in the plane and you want to color them red and blue in such a way that within each axis parallel rectangle, red and blue is balanced. And so in the Lebesgue case, we can achieve the discrepancy log n to the d minus 1 by many constructions, as I have mentioned. Although it's possible that the true exponent is much lower than d. But in the red-blue case, the best exponent achievable so far is somewhat higher, d plus 1/2, which doesn't look like a big deal in high dimension, but in the plane it's quite annoying. So it's 5/2 versus 1. So this would be very nice to improve. So this is an, as I say, almost classical problem. More recently formulated and certainly much less well-known problem is whether one can do anything better if one cannot improve this bound in the worst case, whether it can be improved in the average case, let's say in the L2 case. So can one color points in such a way that a random rectangle that the square discrepancy of a random rectangle will be much lower than log n to the d. That ideally it would be log n to the d half the quadratic average. Here is something is left unspecified here, because if we want to talk about the average, about the random rectangle, we must say what distribution of rectangles we consider. So we can either fix some convenient distribution and try to ask whether this can be improved for that particular distribution, or else it would be nice to find a construction that works for any distribution. So prescribe weights for rectangles, and you want that the quadratic average with those weights is small in the discrepancy. As far as I know, this question has been asked by Verashos, and nothing is known here. So no improvement over this worst case. So this might be one problem that is perhaps more amenable than the previous one. So combinatorial discrepancy can be studied in general as an abstract thing or as an interesting area in itself, and indeed it has been done, and not just by some random people, but by Beck, Spencer, Lovaas, Westergombit, and newest very significant paper I know of is this Chazelle-Wolf. So let me start with a very concrete problem and very annoying problem, which is again well known to many people, I'm sure, but maybe someone who doesn't know it and innocently looks at it with fresh eyes can see some solution. So here the set system are the intervals along 3 permutations. So concretely, the ground set is 1, 2 up to n. You take 3 permutations of the ground set, and the set system are the intervals. For simplicity, I wrote the initial intervals. So in every permutation, you get the first number, the first 2 numbers, the first 3 numbers, and so on. So as is written here. And the question is simple. So is the discrepancy of this kind of set system always bounded, or can it go to infinity if you choose malicious enough permutations? And the best, very little is known. There are several ways of proving an upper bound of log n, but this doesn't help with the real problem. So it's another such problem that is written in many books and so on, but nevertheless very much unsolved, is the Beck-Fiala conjecture. So a Beck-Fiala theorem says that if the maximum degree of a set system is bounded by T, so the maximum number of sets containing any given point is at most T, then the discrepancy is linear in T, 2T minus 1. And there is another, so let me go this way. So the Beck-Fiala conjecture is that it's bounded not only by T, but by constant times square root of T, suitable constant. Or anything smaller than T would be very nice. And what is known is only a bound that also depends on the number of points, and the current best bound is square root of t times log n. So if n is small, it's kind of nice, but if n is very large compared to t, it says nothing about the Beck-Fiala conjecture. And this current record is due to Banaszczyk, and one can perhaps argue that this is not a problem in combinatorics, that it's rather a problem in convex geometry, because first of all, this Beck-Fiala conjecture is a special case of a conjecture which belongs to convex geometry, Komlosh conjecture, and also the current record due to Banaszczyk is obtained by methods of convex geometry, not I don't know of any combinatorial way of matching this bound. So the best combinatorial bound is with this square root ending here. And what is disappointing or encouraging, or I don't know, is that here the LP average for every fixed p can be made square root of t. So given some weights of the sets, of the arbitrary weights on the set system, you can color the points in such a way that the p's degree average of the discrepancy is square root of t. So this is disappointing because it will be probably difficult to prove a lower bound better than square root of t, because all the proofs practically in discrepancy theory use some kind of average, and those that don't use are kind of little miracles. Maybe it's encouraging because perhaps the conjecture is true, and this is an indication that it's true. Let me pass to a not so well-known question, or maybe not so much explicitly formulated question. Is there an approximation algorithm for discrepancy, polynomial time approximation algorithm with some kind of reasonable factor? So of course computing discrepancy, not surprisingly, is NP hard, but can one give some at least very rough approximation? So what would be such a modest goal would be to distinguish set systems that have large discrepancy, roughly close to the n to the square root of n. Well, why square root of n? Because if you have a set system with polynomially many sets, it's known that the discrepancy cannot be much larger than square root of n. So there is just random coloring actually does it. If you have polynomially many sets, if you have m sets, you can color with square root of n times square root of log m. So if m is polynomial, then there is just a polylog factor times square root of log n. So that's why I just wrote square root of n here. And can one distinguish by some kind of algorithm this kind of set systems with almost the highest possible discrepancy from set systems that have low discrepancy, n to the epsilon or log n, or very low discrepancy? And here I wrote her-disk instead of disk, hereditary discrepancy. Here is a little explanation. So this hereditary discrepancy is the maximum discrepancy of a system induced by some subset. So you choose some subset y of the ground set, you restrict the sets on that y, and you compute the discrepancy, and then you take the maximum, and this is the hereditary discrepancy. Why this kind of provision? Well, because with discrepancy without hair, one can cheat. One can, for example, take a set X and divide it into two halves and think of that this will be colored red and this will be colored blue in the future, and then put only sets that are exactly half-half. And you can put very complicated any set system here and a mirror copy here, and you get discrepancy 0, but this is cheating, so this is no good set system. So that's why one should speak about hereditary discrepancy. And as far as I know, nothing is known in this direction. So there are approximation algorithms for related things, some kind of integer rounding of packing programs and this kind of things, and nice results and powerful results. But in that more general setting, what they approximate, there is some quantity that they approximate with some good error. But here for the discrepancy case, this approximated quantity would be 0. So even if the relative error is very small, it's no good. So kind of, yeah. So these things are nice, but they don't seem to be of any help here. So this is, I think, in a sense, a central question in this combinatorial discrepancy, as I would understand it. And there are many more questions. For example, there is the annoying question again. What happens if you have a set system and add just one set? So we have a set system where the hereditary discrepancy is small, some delta, and we add one single set. And how big discrepancy can we get? So can it be that can the discrepancy grow by more than a constant, let's say? I think this is wrong. It should be multiplicative. So we thought about this problem with Fu-Ha Wan and with Jong-Han Kim, and we did not get very far. We just proved a bound, as is usual in those annoying problems, that again depends on the number of points, which it should not, but here it does. And it shows that the discrepancy can grow by at most a factor of log n. Probably it cannot grow at all by this much, but on the other hand, it's at first sight it's not obvious at all from this assumption that the hereditary discrepancy is bounded can be used at all in. So if you add a new set, how do you use the assumption that all the restrictions to all subset can be colored nicely? So let me give the proof of this result. It's a very short proof, and even Friday afternoon talk should contain some proofs. And I give this proof because it also uses the most powerful method for upper bounds in combinatorial discrepancy, which is Beck's invention, the partial coloring method. So here I will be hopefully able to demonstrate it in action to some extent. So we have a set system where the hereditary discrepancy is bounded and we are adding a single set. So first of all, we may assume that this set is the whole ground set. It's simple reduction that if we can do well for the ground set, then we can do well for any set as well. So what is the problem? We can for any given subset y, we can color the points of y red and blue in such a way that every set of f is rather balanced, but we don't know anything about the whole set, because this presumably does not belong to the set system, and so maybe every coloring that balances all those sets of f must be such that there are many more red points than blue points, or the other way around. So the trick to get this, at least this upper bound log n times the original discrepancy, is that first we show that there are many colorings that do well on all the sets of f. Namely, why there are many colorings? Well, because for every y, there is a coloring restricted to y that does well on every set. And there is also a coloring on the complement of y. And these colorings can be combined in two ways. So if one says it in the red-blue terminology, then if we have a red-blue coloring here, some red-blue coloring here, and some red-blue coloring here, we can combine it into a coloring of the whole set in two ways. One of them is that we retain the colors, and the other is that we switch colors on one of the halves. This provides many colorings. How many? Well, n to the 2 to the n half can be easily shown. And what to do with so many colorings with this discrepancy? Well, this is where the partial coloring method comes in. If we have many colorings, then there are two of them that differ in many coordinates, that differ on many points. This is just some fact about the combinatorial cube, that a large set has a large diameter. And moreover, if we classify those coloring into rather few classes, depending on what discrepancy they give for the whole set, which can be large but not larger than n, so we have n classes. So we find that there are many colorings that give the same discrepancy to all of x and discrepancy at most 2 delta to every set. So let's take such two colorings that have the same discrepancy on x, and let's take this combined coloring. Well, this needs a little explanation, since I've been talking in terms of red and blue points all the time. But this notation assumes that the red points are +1s and the blue points are -1s. Then we can combine them in this way, and we see what happens. So if there were 2 red points, we would get a red point. If there were 2 blue points, we would if there was a red blue, we get red. If there was a blue red, we get blue. But what if there are 2 red and 2 blue? Then we get 0 here. So not all points will be colored. Some points get 0, some points get reds, and some points get white. But because chi1 and chi2 differ on many coordinates, at least some small constant times n points are colored by this trick. And the discrepancy of the whole set by this, since these two had the same discrepancy on x, then if they are subtracted, the discrepancy cancels out. And the result is a coloring that has 0 discrepancy on x, and at the same time it colors many points. So it's not a full coloring because there are those zeros, but it's a partial coloring where at least 1/10 of points are colored. So far the discrepancy is at most delta, but only part of the points are colored. So now this procedure is iterated log n times, and in log n steps we get coloring of everything, and the discrepancy in the worst case can accumulate, so adding delta in every step, and this results in delta log n altogether. Okay, so this is the short proof. And now in this spirit, one can ask what happens if one adds more than a single set, if one has 2 set systems with some bounded discrepancies. So again here it should be hereditary discrepancies. So for example, whether the discrepancy of the union can be bounded by some function of the hereditary discrepancies of the 2 systems, the answer is no. But as far as I know, there is just a single example, very clever example due to Hoffman. Here it's painted. So the ground set of our example are the edges of complete, K array 3 of depth K. So here I tried to make a tree of, not quite. So here there are four branches, so there should be 3 branches, then it would fit better. So there are 3 levels and 3 wise branching, but in general you have k levels and k y branching. And what are the sets? Where in one system the sets are all passed from a leaf to the root, and in the other set system the sets are the neighborhoods of a vertex. So all edges coming down from a vertex. And now each of those systems individually can be colored nicely. Even if you delete some vertices, it can still be colored nicely. But the combined set system cannot be colored nicely, because if you have a tree with edges colored red and blue, then there is either a monochromatic path or a monochromatic fan of a vertex, as is very easy Ramsey's theorem. Very easy to see Ramsey's theorem. But this is a very particular kind of example. So are there other types of examples, and how bad can this discrepancy be? So a natural conjecture would be that the resulting discrepancy of the union is bounded perhaps by the sum of the discrepancies times log n. but it's not clear how to do that. Okay, let me spend some minutes of your valuable time by talking about something else. Again, just reminding some problems that are not, this is not quite already discrepancy theory, but it's related because, again, you want to place points nicely with respect to some class of sets, but this time you don't want to approximate a measure. This time the goal is just to hit all big sets. So concretely, we are given a probability distribution, some mass distribution in the d-dimensional space. And we want to construct a small set of points such that every convex set that has measure at least epsilon intersects this small point set. And f of d and epsilon is the minimum size of such an n that one can always construct for every. So the enemy gives the measure, the mass distribution, and you can always construct this big a set. So it's not at all obvious that such a set can always be constructed. A finite set can be constructed, but it's true and non-trivial result first proved by Alon and others, I think. So a starting example for thinking about this problem is that you take the measure to be just the uniform distribution on the unit circle. Then the goal is to place points somewhere in such a way that whenever you have a piece of the unit circle of measure epsilon, of total length epsilon, make the convex hole, then one of your points is inside. So here, order of 1 over epsilon points are enough, but even in this rather simple situation, this is a non-trivial result. It's not easy to see. Here is a summary of what is known. So for fixed d, the upper bound is epsilon to the minus d, some polylogarithmic factor. Chazelle at company proved this first, and with Uli Wagner we have some simpler and somewhat more general proof. And for some special cases which might be thought, which I actually, for example, thought that might be candidates for a good lower bound, there are results that show that in those special cases you can construct a weak epsilon net of size that is of linear size, almost linear size, not quite linear. So those cases are the moment curve, so uniform distribution on a piece of moment curve, or any distribution on the moment curve, or the unit sphere, a generalization of this. So there is an almost linear upper bound. But on the other hand, there is no non-trivial lower bound, and the question what happens, for example, in the plane, the best upper bound is 1 over epsilon squared, this time without log factor, but anything below that would be very nice. Don't know how to do it. Let me mention a related or a special case of this problem, a slightly different look at it, which is what happens if the dimension is large. So far in all those questions, the geometric questions, the dimension was small. But here we let the dimension go to infinity, and we can fix epsilon to some small constant. And so what is the order of magnitude? So what is known is written here. So from below, it's e to the constant times root d. From above, it's e to the, like d to the d. So e to the constant d log d. So what is the truth? And in particular, the example used here for e to the constant times root d is the uniform distribution on the unit sphere. And even for the unit sphere, it's not clear, and I think it's a very nice problem in high-dimensional geometry. So you want to place points within the unit sphere in such a way that anything, and if you choose an epsilon portion on the surface of the ball on the unit sphere, then the convex hull intersects one of the points. So here is an indication of the proof by e to the, how to get e to the root n. So the setting is, so once again, this green thing is the unit sphere, not particularly round, but this is what it's supposed to be. and the enemy places a small number of points, and we want to show that this is not a weak epsilon net. So we want to show that there is a convex set which is large but avoids the point set. So how do we make such a convex set? So we try to cover the points by a union of half spaces in such a way that those half spaces altogether leave at least epsilon portion of the sphere untouched. And here is the construction for such a thing. So we choose some suitable radius, and we distinguish the points, the green ones given by the NMA, into two classes, the outer points and the inner points. For the outer points, we use an individual half space for each of them to cut it off or to cover it. So these half spaces are indicated here. You might wonder why they are so much curved. Even someone very bad in drawing as me could perhaps make a more straight half spaces, but the answer is that this reflects the reality in higher dimension. Not that half spaces would be curved, but they cut off very small pieces of the sphere if the point is close to the surface. So the points that are kind of sufficiently way out from the center, they can be cut off individually, and not much of the sphere is used by all those caps altogether. And the points inside, they are cut off by a common half space. And the thing is that if we don't have too many points in the inner sphere, then we can cut sufficiently deep into it. And this half space, the complement of this half space, leaves still sufficiently large part, epsilon part of the sphere uncovered. And if one does the calculation, so one has to find out what is the radius. This is what one arrives at, but this is a somewhat primitive construction, so probably there is a better way of placing points. I don't know. So much for weak epsilon net. And in the remaining few minutes, another problem that again is not so, that is more recent but also known probably to some people, and this is conflict-free caroling, which looks like a discrepancy type problem, but my impression is that it's rather different from discrepancy. But nevertheless, it's a nice problem that deserves some more publicity. So what is a conflict-free coloring? So we are given points in the plane, n points in the plane, and we want to color them by small number of colors, in this case 1, 2, 3, 4, in such a way that if there is a rectangle, axis parallel rectangle, that is not empty, so it contains at least one point, then there is a color such that this rectangle contains exactly one point of this color. This has some sort of practical motivation. So if you have a transmitter for mobile phones or something whose range of reach is exactly a rectangle, which is rather atypical, I think, then, and these are the users. No, sorry. This rectangle is what a mobile phone user can reach. So the transmitters that he can connect to, and you want, these are frequencies, these colors, and you want every user, no matter where she is, to be able to have a to pick a frequency that such that there is only one transmitter with this frequency within his or her reach. So this coloring, notice as an exercise that this coloring is bad. This is not the coloring as it should be. Why, for example? Because of this rectangle. Right. And the question is, how many colors can there be? How many colors are needed? And while for some reasonable ranges, for some more reasonable models of transmitter ranges, as for example circles or circular disks, there are very satisfactory and rather precise answers. For those rectangles, it's not clear and it's rather annoying open problem. So the lower bound is little more than square root of n, and the upper bound is n over some little polylogarithmic factor. So not exactly n, not exactly square root of n, but still a huge gap. And we have been working especially my student Aleš Přívětivý has been working on this problem. He did not get any farther with the bounds, but we realized a connection which is also surely known to people working on this problem, but nevertheless I say to a problem in partial order theory. Namely, the question is more or less equivalent to what is the independence number of a Hasse diagram of a two-dimensional poset. So what is a Hasse diagram? A graph G is a Hasse diagram of a poset if there is a partial order on the vertices such that the edges correspond to the relation of being immediate predecessor or immediate successor. So this is a typical partial order. So the subsets of 1 to 3, and the Hasse diagram is the cube. And here, so we look for the independence number. We could also look for the chromatic number, but independence number should perhaps be simpler and up to a log factor. In this problem, these things are equivalent. And so let's write G2 of n as the minimum over all such graphs of the independence number. How big this can be, how big independent set can you always guarantee in this Hasse diagram. And what is the restriction on the partially ordered set? It is this dimension 2, which means that there are two partial orders, two permutations of the or two mappings, two bijections of the ground set of the two mappings of the vertices into 1, 2, 3, and 1, 2, 3, 4, and up to n, such that the ordering relation x precedes y is equivalent to inequalities in both coordinates. So there is also a geometric picture in the plane or various other illustrations. So this is the usual dimension, Dushnik-Miller dimension. And the somewhat interesting thing is that this same question is not clear even if we drop this two-dimensional restriction. So we can define G of n as the minimum size of the independent set in a Hasse diagram on n vertices. There, something little bit is known about this, but not a great deal towards solving this question. So first of all, it's known that this function G is sublinear, somewhat sublinear. This is a construction due to Brightwell and Nechetriel, but their construction is not two-dimensional. It has high dimension. So there is no sublinear bound. It can be that for every fixed dimension, this function is linear. About two-dimensional posets, it's known that the chromatic number of the Hasse diagram can be arbitrarily large. This is a beautiful construction due to Kříž, but this construction has very big independent sets, and as a function of the number of vertices, the chromatic number grows extremely slowly. It's some log star or something like that. So this is my list of open problems.
Thank you very much for the interesting talk.
Good.
Other questions?
Is there any possible connection between the original sort of continuous discrepancy problem and things like generalizations of spherical designs?
Generalizations
Generalizations of spherical designs?
it's quite possible, but there are. Yeah, I don't know about this particular connection, but people explored many things, many kinds of constructions. So explicit, it seems very difficult to do anything by explicit construction. There, this has been studied very, very, very much, but perhaps some semi-random thing could. I don't know.
About the problem of differentiating between different code orders. You asked this question, is a polynomial algorithm, but the definition of discrepancy was, the orders of, you compare them asymptotically, right? So you have infinite number of points. So
Well,
that the actual data giving rise to a model that predicts this geometry for the centroid behavior. And when you, I'll just leave this final one up, that this is it here in more detail. The different curves here, this would be what you get for a point source, and then these curves that are close to each other are the answers you get, which are essentially the same when you have different brightness profiles for the source. It turns out you can get a similar but different geometry in the case of a cusp. And the equations that you use for this explicit equation, for this explicit curve, it not only gives you a picture, but you can apply that equation to determine the angular radius